So some of you may remember one of my earlier videos where I made a DIY power pack to power my telescope, and I mentioned in the video that I would also later modify the actual power pack so it has dual heater controls. Well, in this video I'm going to explain how I've modified this power pack to include dual heater controls, in this case 6 channels, and I'll explain why I've actually made my modifications. Well, out here in the UK it's getting quite cold, and when you go out at night it might be a clear night, but your experience is ruined because you keep getting dew either on your eyepiece or on the internal mirrors in the actual telescope. So the cure to this is a dew shield, or a whole load of heater elements wrapped around your eyepiece, around the actual telescope, or around the actual viewfinder and finder scope. But if you do this and you've got heaters on your eyepiece and on your mirrors and your finder scopes, you're going to have a whole load of cables all over the place, and it doesn't look very neat. So I wanted to actually incorporate these into the actual telescope. So I'll have one cable that just plugs into the telescope, and that's it. There won't be cables all over the place, and it just looks a lot more neater, and it's actually a lot more lighter also. And that's what I've gone and done. Now, on the actual power pack, I've included the actual channels, so I can actually adjust the heat to 6 individual elements off of the actual power pack. Okay, so what have I wired up? I've wired up a heater element for the actual primary mirror, the secondary mirror, your lens, your eyepiece, and also the finder scope and the viewfinder. By doing so, I've got actually control throughout the whole range. I don't have to worry about anything building up with dew or anything. I can adjust the temperature, and certainly when it warms up I just turn the dual heater control all the way down, and it actually saves power. I've used pulse width modulation because it's far more efficient than engine, and I'll go through the theory in this video. So one of the other advantages of using this method, it's a lot cheaper. If you build your own dew heaters, it's a lot cheaper. If you go out and you buy a dew heater controller, the actual controller on its own is going to be £100, and you're looking at spending an additional 20 quid per element that you buy, per blanket, per heater blanket that you actually buy. So you're going to spend 20 quid for your eyepiece, you might spend 20 quid for your mirror, your primary mirror, 20 quid for your secondary mirror, if you can fit one onto your secondary mirror. I don't know, I don't think there's one on the market that you can buy for your secondary mirror, not without modifying it. But it works out quite expensive. With what I've built, I've probably spent less than £100. Each actual channel, PWM channel for the actual dew heater probably cost me about £4 to £5, okay, and they're 2 amps each. But you're not going to run up to 2 amps. No, each one of my ones runs at about 1.1 amp. So essentially what I have is 6 individual PWM controllers, and I've just wired them up in parallel, and I've took a live off of the positive on my power pack, and I've added a switch and a fuse, and I power up all 5, but each individual channel has a control. For example, it might be just the eyepiece, it could be the secondary mirror, or it could be the primary mirror, or perhaps one of the viewfinders. So this is the schematic that we're going to be following. These are pulse width modulations modules. They're actually these, and you could control the actual heat of the dew heaters with this variable resistor, a potentiometer. Bear in mind that this is not actually controlling the heat, this controls the actual frequency, which I'll explain later on. This is the actual circuit which we're going to use, and this is actually an extension of my old circuit which I had here. So basically you've got the first switch here which closes, that's this switch here, and then here you got your cigarette lighter, okay, and your voltage meter. Well, this new circuit will connect here, which is basically there, okay, and then it extends over to the joule heater section, all right, but I'll explain that later on. If you don't understand this circuit, just go over to my first video where I showed you how to build the actual power pack, and that will explain how everything works here. Okay, so look, we're going to use 14 watt elements in this joule heater. We don't want to go much more than 14 watts because it will get too hot and you might end up burning things or starting a fire. Okay, so we need to know what the resistance is going to be of these elements, okay, because if you don't get the resistance right, you're not going to be able to get 14 watts. So how are we going to do it? Well, we're going to use these triangles to help us. Okay, here's what all the letters stand for. So we know that we want 14 watts. 14 watts of power. So we're going to come over here. We've got P, so we're going to replace P with 14. We also know that our Dew heaters work with 12 volts because we're using 12 volt batteries. Okay, so if you do the maths, 14 divided by 12, you're going to end up with 1.16 amps. Okay, so we now know what our current is and what our voltage is. So now we're going to come over to this triangle. So we've got 12 volts divided by I, which is current, and we know our current, which is 1.16 amps, which will account to 10.34 ohms. But you're not going to get a resistor which is 10.3 ohms, so we now know that the resistance needs to be 10 ohms. Okay, now if you look at my circuit here, we've got our pulse width modulation module, we've got our cables coming out to a heater element. Okay, this is nickel chrome wire, or nichrome, and the resistance of the cable needs to be roughly 10 ohms. So what do? You get your multimeter, you put it onto resistance, and then you undo your wire, yeah, like this. Put your crocodile clip there and another crocodile clip there, and keep extending your wire, looking at your multimeter, which will be set at on resistance until you get to 10 ohms. Okay, so we're not going to use a resistor like some people are using. Using resistance is not very effective. Basically, you're going to waste energy just heating up the resistor, which is not a good way. So the correct way is to use nickel chrome wire, which is what you will find in heaters and toasters and things like that. Okay, so use this. Mine's 0.45 millimeters in diameter. The thinner the wire, the higher the resistance is going to be. So you should take that into consideration, because if you're making a large coil, you're going to want to have thinner cable, so it's actually a little bit longer, thicker cable, yeah, so it's longer, and then you can get more coils round. But if you're working on something where you don't have much space or something like that, and the cable needs to be shorter, well, to get to your 10 ohms or the desired resistance, take the thickness into consideration, because the thinner the cable, the thinner the wire, the higher the resistance is going to be. Okay, so yeah, that's it there. When you're going to connect these, don't solder them, because when it gets hot, you know, I mean, it's not going to melt, but it's not advisable. I would just use screw clamps, you know, like off of I think they call them chocolate blocks or something like that. Do a mechanical connection. Okay, don't solder it. Use a mechanical connection. I'll show you as I could go along. All right, so there's our equations. Easy, simple, elementary, you know, simple maths, nothing difficult. If you've got any questions about the actual schematic, just send me a message below and I'll be happy to help you. I mentioned I would explain how the pulse width modulation is actually working and what these modules are actually doing. Well, pulse width modulation, all you're doing in pulse width modulation is you're turning the power on for a certain time and then you're turning it off for a certain time. But this happens so quick that your eye wouldn't be able to tell the difference. For example, if you were looking at a bulb and you turned the knob 50% down, then the brightness will go down 50%. But if you turn it to 100%, then the bulb will be very bright. And then if you turn it all the way down, the bulb will just go off. But you wouldn't be able to see the pulses being applied to the actual bulb. So what I mean is, let's say we have a curve. Okay, and we said we're going to run 1.16 amps over 12 volts. All right, so this is the amplitude, this is the time, yeah, the frequency. So we're going to be on for 50% of the time, off for 50% of the time, on 50% of the time, off for 50% of the time. Okay, something like this, and it ends up forming a square wave. Now this is 50%. Yeah, so the knob will be halfway and the light bulb would just be not full, but you know, running at 50%. Okay, but if you turn the knob all the way up, the light bulb would be very bright. Okay, and all you would have on the graph is just a straight line because you're on 100% now. Okay, so you'll be applying 12 volts at 1.16 amps all the way across full whack 100% duty cycle. Okay, this you know, when we're talking about pulse width modulation, we're talking about in hertz. So obviously this switching happens very fast, like thousands of times a second. Okay, so you wouldn't be able to see it going on and off, on and off. Like you looking at the bulb, you couldn't tell. Okay, so what if we were running at 25%? Well, you've got your graph here. Now we're going to be off for a longer period of time, and we're going to be on for just 25%. Okay, so can you see it's going to be half of the on. Okay, on 25% of the time, off, on. Yeah, so you're reducing by turning the knob further down, you're reducing the on time even more. So this is what is referred to as pulse width modulation. It's done with microcontrollers and transistors. Okay, there's thousands of little transistors in the microcontrollers and they're constantly switching, and you end up with a pulse width like this, and you're just basically affecting the on time and the off time, and what you get is an average coming out. Now this is a lot more efficient than using a resistor to block how much energy is going to go to the actual coil, okay, to the actual heater element. Why? Well, think of it like this. Okay, so you got your cable, okay, and then you've got a resistor here, and what's happening is you've got 12 volts going into the resistor at full whack. Whatever current comes into this resistor, okay, and then what the resistor does is it restricts the current flow, so only 1.16 amps could pass through this actual cable to the element. But what's happening is all this other energy inside this resistor is getting burnt up and it's getting wasted, so that's not very good. But if you use a microcontroller, what the microcontroller does is it switches it on, it switches it off, switches it on, switches it off, so you're not wasting any energy. So using PWM is much more efficient. That's the best way to think about it. That's the way I understand it. But those of you who know electronics better than me or power engineering, go ahead, comment, educate me and educate everyone else that's watching the video. But this is just basic pulse width modulation as I understand it. It's been a long time since I've studied this stuff, so forgive me if I've got a few things wrong. Okay, so we've done the theory. We know what resistance our nickel chrome wire needs to be, which is 10.34 ohms. We've got a multimeter which we're going to set on on resistance. Okay, that's on resistance. So we've got our nickel chrome cable. Alright, so we'll put one end here, one end of our test lead to the end of the wire, and the other end here. We can see that this length here has 1 ohms, but we need 10.34 ohms. So we're going to extend the cable, run the crocodile clip along the wire until we get to about 10.3 ohms. Okay, almost there. 7, 10.36. Back it off a little bit. 10.3 ohms. Okay, so what am I going to do? I'm going to cut it from here. I'm going to thread it through some heat shrink, shrink it, and then I'm going to use it to wrap it around the circumference of the primary mirror. And the idea is not to heat up the actual mirror, but just to heat up the inside of the telescope a little bit, and that will stop dew from building up on the primary mirror after a long period of use. Okay, so I've gone ahead and heat shrinked the wire, and I've just wrapped it around the circumference of the mirror like this. And all we're going to do now is just wire it up to the pulse width modulation units, and we'll take some measurements to see if the theory matches actual real life results. Notice that the cable is not too long. As I said, you're not trying to heat up the actual mirror because that will give you a distorted view, and you don't want to make it too hot neither because you don't want to run the risk of fires or anything like that, which is why we're only using 14 watts. Don't go any higher. I'm not going to be held responsible for any fires or if you mess up or anything like that. If you're going to do this, do it at your own risk. Okay, I'm going to take some measurements in a moment. I'm going to basically measure the current and the voltage and see if the actual true life figures we get are similar to the actual calculations that we calculated earlier on in the theory. Just want to show you the actual setup and what I've done. So basically this is the telescope which I built. It's made out of fiberglass. There's a separate video on how I actually put this together that you guys could search on my videos if you like. You can see here I have a heat element wrapped around the actual finder scope, and I have a heater element around the actual scope which I use for star guiding with PhD. There is also going to be a third connection here, which I'll probably do just here, which will be for a separate heater controller that will go around the actual eyepiece, which I haven't done yet, but the actual connections are here anyway, but I haven't got around to doing that. And I don't know if you can see that, but it's not finished. There's the wiring at the back, and there's a cable that goes all the way down. Can you see the cables that run all the way down the inside of the tube, the telescope tube? Okay, so they come down to I think it's a 10 pin, okay, 10 pin cable, and it goes all the way down to the power pack, which we modified, and we've got individual channels here which are controllable. I've got 6 channels. I'm going to explain why later on. You can see here that, you know, we simply just unscrew it and it pulls off. You can see at the moment the power pack is at 12.3 volts, and if you look closely, I've got USB outputs also, so you could charge your phone or other devices from the actual power pack also if you need. So yeah, let's take a look now at the actual figures and see how we're doing. Okay, so at the moment, with the dew heaters off, the whole system is drawing about 3 milliamps, 3-4 milliamps max. I'm going to switch on the dew heater now, and let's just get the range right. Okay, so I'm going to turn it up full whack to begin with, so we get 100%, and we're getting 1.13 amps of current draw at full whack. Oh, 1.12. Okay, and we calculated that would be drawing 1.16 amps originally, so we wasn't too far off. Okay, voltage is at 12 volts exactly at the battery pack right now. Okay, let's see what happens when we turn the actual power down by half. Let's see if we how much current will draw. So that's full. This is off, so half is about there. 0.7 milliamps, 0.71 amps. Okay, and if we go a little bit more at 25%, we're drawing 0.48 amps, or 0.5 milliamps, or half an amp. So there you have it. That was the theory to the actual wiring with regards to how the pulse width modulation dew heater controller works. I ended up using one of these USB adapters, which also displays the voltage. It's actually a fast charger. I ended up using these connectors for the actual main cable. It was a 10 core cable, I believe. This is the pulse width modulation unit that I actually used. I ended up using 6 for 6 individual channels. You need one per channel, so if you're going to use two, if you're going to have a 2-channel unit, you're going to use 2 of these. If it's going to be 5, you're going to have 5 of these. And if it was 10, I don't know what you're going to need 10 for, but if it was 10, you would need 10. With regards to the other parts, I think you could probably find the other parts in my video on how to build the actual power supply unit from the first video. But if you've got any questions, please ask me. I'm happy to help, and like and subscribe, help me, and I'll help you. I'll continue to make these videos. I hope you enjoyed it. I'll see you on the next video.
Perfect.